Hi, I'm Steven Feuerstein, and I write practically perfect PLSQL.
Greetings and welcome to the PLSQL channel, a series of video trainings on the Oracle PLSQL language. My name is Steven Feuerstein and I'm a PL/SQL developer just like you. This lesson is part of my series on programming with collections, Oracle's array-like structures, and the focus of this lesson is working with associative arrays. So, this lesson focuses on associative arrays, one of the three types of collections in the PL/SQL language. An associative array is a variable declared from an associative array type, which doesn't tell you a whole lot by itself, but here's an example of a type declaration for an associative array type of data, in which you see an isTableOf clause that specifies the data type of each element in the list or associative array, in this case a list of strings, and an indexBy clause that specifies the type of indexing. And we'll get into lots more details on every aspect of this type statement, but whenever you see isTableOf and indexBy, that's an associative array. Now, with a little bit more descriptive information, let's look at the PL/SQL User's Guide definition of an associative array. It's an unbounded set of key value pairs. Each key or index value is unique and serves as the subscript, essentially the location of the element in the array. And you can access elements without knowing their positions in the array and without traversing the array. What does that all mean? Well, essentially, what it means is that when you declare an associative array, you specify the indexing, in this case, indexing by integer, and you specify the data type of the element. Now, what you see here is a diagram of a list of strings. Index value 1 has the value apple in it. Index value 22 has the value pear. Index value 100 has an element orange. And index value 10,023, the word apricot. And what all of this means from the Oracle documentation is that if you have the index value, if you've got that number 22, then you can go right to that row or element within the associative array without scanning through the array, the traversing. And without knowing its position, there's not really a sense of position, it's simply an index value. So that's the general description. You've got key value pairs, index value, and elements. And Oracle allows you to go directly to those different elements without a traversal of the collection. A little bit of background on the associative array. It's actually the first type of collection ever introduced into PLSQL. Way back in Oracle 7, Oracle introduced something called the PL/SQL table. That's why you see in the syntax of the type statement isTableOf. They were actually called PLSQL tables originally. Then in Oracle 8, when Oracle added nested tables and V-arrays to other types of collections, which I'll be talking about in separate lessons, Oracle changed the name to indexBy table because the distinguishing characteristic is the indexBy clause of an associative array. And then in Oracle 9i, Oracle renamed them to associative arrays with the advent of string indexing. And if you look at Wikipedia or other sources for definitions of IT terms, you'll find associative array in the context of being able to associate an element, whether it's a string, a number, a date, etc., with its index value, and the index value could be a string or an integer, which is certainly true of associative arrays in PLSQL. So that's a little bit of background. Also, partly because of the original origins of the associative array as the PL/SQL table, these associative arrays can only be used in PL/SQL blocks, in contrast to nested tables and V-arrays, which can be actually used within the SQL layer even as the data type of a column in a relational table. That's not possible with associative arrays, only allowed to be used in PL/SQL code. Let's take a closer look at some characteristics of associative arrays. So again, the key indicators of an associative array declaration, or the type, is that you've got isTableOf and then the indexBy clause. So the table of data types, what is it a collection of? A collection of dates, strings, etc. Can be almost any valid PL/SQL type. And I'll come back to that and talk about the exceptions in a few slides. But essentially anything you can declare as an individual variable, like a string, number, date, record, object type, can be the data type in the table of clause of an associative array. The index by clause, specifying the type of the indexing in an associative array, can be integer or string. And that means that you can essentially index by anything, because you can convert just about anything to a string. Index values can never be null. If you try to use the null value as an index location, Oracle will raise an exception. And very importantly, associative arrays can be and often are sparse. And that means that you do not have to populate elements in the collection in consecutive index values. Index value 1, 2, 3, 4. You can use whatever values you want within the valid range, which I'll talk about on the next slide. So this ability to not have to sequentially fill or densely fill your collection results in lots of interesting advantages. Particularly, you can easily emulate primary keys and unique indexes from relational tables as indexes in your associative arrays, since we often use integers, sequence-generated integers, as our primary key values. Let's take a look at a simple associative array example. In this piece of code, I declare a list of strings, maximum size 20, indexed by integer, and my variable based on that type is called the happy family. So happy family, and then I use the name of the type, just like I would declare a date or a string or anything else. I then populate my collection with multiple values, and then I iterate through my collection to display those values. Now, rather than spend more time on this screen, let's go ahead and take a look at the file from within Toad. So there's my associative array type. I know it's an associative array because I've got the index by clause. I've indexed by integer. I've declared a variable of the same type. Then I've got 4 lines of code to assign values, assign elements to my index values. And what I'm showing you here is the fact that you have complete flexibility. I hope you never write code that looks like this, with hard-coded literal values for indexes, with crazy numbers like, oh, let's use negative 15,070 as one of my index values. But simply to demonstrate that you can do this. Collections, associative arrays, can be sparse, and this is certainly a very sparse collection. So I've got a few hard-coded assignments of index values. Usually your code will look something like this. You've got a variable called your index value. You might assign it a value, or it might be calculated somehow. And then I use that as the location for the name. And in fact, what I'm putting here are the names of the members of my immediate family, my 2 children, Eli and Chris, my wife, Viva, and myself. Okay, so I assign the values. My collection now has 4 values, and in fact, let's verify that. Let's display the happy family count using our method, the count method. So we'll see how many rows are in the collection. And then what I want to do is iterate through all the rows of the collection and display the name at that location. So in the separate lesson on collection methods, I talk about the various methods like count, first, next, and so on. So if you're not familiar with these methods, watch the lesson on collection methods. But what I'm doing here in this code is saying, well, get the first or lowest defined index value. While that index value is not null, which means I haven't gone to the very end or the collection is not empty, then I'm going to display the name at this index value, and it's equal to, so I go to the collection, I go to that location in the collection, and this returns a string. It's a standard 3GL syntax for looking up a single dimensional array value. And then after I display the value, I call happyfamily.next. I say, go to the next defined index value. I pass it the current one. And it says, well, what's the next highest defined index value from that point? When I get past the end of the collection, when I'm at the end of the collection and ask for next, it returns null. And then my loop will stop. And in fact, when I run this code, I see the following. I've got 4 elements in my collection, and from first to last, the first is negative 15,070, then 1, then 3, then 88. So there's the order defined by my index. And if I want to go from the last to the first, I can say start with last and use prior to go to the previous value. And now if I run my code again, I'll see the data in the opposite order, going from the highest to the lowest. So these are examples of using the methods first and last, next and prior to navigate through a sparse PL SQL collection. I have not defined my index values 1, 2, 3, and 4. I cannot trust, for example, a numeric for loop to do the job for me. So for example, if I declare and populate my collection in this way, non-sequentially filled, if I try to use a for loop, I'm going to run into trouble. Because what this says is go from every value between first and last, first being minus 15,070, last being 88, and touch every single integer value between those two. And as soon as I get to a value that doesn't exist, well, as you probably know from seeing previous lessons, I get the no data found exception. So when you're not using a densely filled collection, when it might be sparse, when there might be gaps in the collection, never use a for loop to iterate through the values in the collection. Instead, use that while loop. And the while loop will automatically skip over those undefined index values. So that's an introduction to a rather simple associative array, just a list of strings. Of course, things can get a lot more interesting than that. Let's take a look at an associative array of records. Here's a piece of code that demonstrates how easy it is to emulate a relational table inside your PL SQL code. So in a single type statement, I specify a new type of data, employees AAT, associative array type, is table of. Now instead of a string or a date or a number, I'm going to use an entire record from the employees table. So whatever the employees table looks like at the time my code is compiled, every element in this collection should have that same appearance, same structure. And I'll index by integer. I declare a variable based on that type. In my cursive for loop, I say get all the data from the employees table, take each record from the employees table and assign it to my employees list. And I specify as the location in my list employees count plus 1. This is a way of sequentially filling my collection. Count starts at 0, so my first record retrieved goes into index position 1. Then the next time I come around and get the next record, count is 1, so 1 plus 1 is 2, 3, 4, 5. So I add elements sequentially to my list. So as you can see, it doesn't take very much code to accomplish a fair amount of work. Automatically create a structure that mimics the structure of my relational table. In a simple cursive for loop, or even more simply, with a bulk collect operation, I can populate the contents of my collection from the table. Let's take a look at some more of the variations possible with collections of records. So here's my type declaration for an associative array that mimics the structure of my employees record. And what I'm going to be doing is indexing by integer, which could be sequentially indexing, or it could be, as I'm about to show you, emulation of the primary key. Next, let's take a look at your first example of a string index collection. So a table of employee records indexed by the employee last name. So now instead of indexing by integer, I'm going to index by string, by the employee last name. Finally, just to show you that you can do it, you don't have to just have tables of records percent row type. I can declare my own user-defined record and use that as the data type for my collection. So this is just the ID and the name in a list, indexed by integer. So all those things are possible. Let's take a look at how I can use these different collections. First of all, even though I've declared this collection as the type based on employees percent row type, it doesn't mean that I have to populate a variable based on that type from the database. It's a piece of programmatic data. I can simply say, well, now that I've got my collection defined, I'm going to populate it myself. So Feuerstein is the last name of the 77th row, or index value, in the employees list. So you can manipulate these things programmatically. You can populate them from tables, which is what I'll show you in the rest of the script. It's up to you to do that. But once you've declared it as a variable inside your PL SQL code, you can use it directly inside PL SQL, completely separated from or ignorant of data in the table from which it was defined. Now, first what I'm going to do is go through all the rows in my table and assign that record to the list, basically adding it sequentially to the end of the list as I showed you before, count plus 1. So the first record goes into row 1, then row 2, then row 3. Then after that, I'm going to show you how many rows I have, the count in my collection, and the last or highest defined index value. And as you can probably sort out rather easily yourself, when I fill sequentially from 1, the last and the count should always be the same. Next, I'm going to do the same thing, populate my collection sequentially. But instead of using a select star from inside my for loop, I'll reference a cursor. So I've declared a hard-coded explicit cursor, select star from employees. Now in this loop, again, for every record I find, I'll take that record, add it to the collection, and what I'm going to do is simply use %row count. It'll achieve the same effect as count plus 1. I'll have a sequentially filled collection starting in row 1. The difference is that if you use %row count instead of count plus 1, your code will run faster. It's a bit more optimized. Now, generally speaking, the difference in performance time is not something you would notice unless you've got lots and lots of rows of information. But if you do an explicit cursor, you're better off using %row count than count plus 1 if you're filling sequentially. So I filled up my collection actually twice with two different ways of accessing or specifying the row number. Now, let's take a look at referencing the elements in a record. So this is a collection of records. This gets me the first defined index value in the collection of records. So this whole thing right here is a record. Each element in the employees list is a record. Therefore, I can reference individual fields of that record by using dot notation and then the name of the field. So here what I'm doing is saying, well, I don't care what the last name of the person in the first index value was. I'm going to assign it Feuerstein so I can override the existing data. But the main thing I want to get across here is how you specify the elements or the fields within a collection of records. It's the same thing you've always seen, record.field, but now the record is often expressed as a much more complex kind of expression. That can take some getting used to. And after I do all that, I'll show the row count, last and count. It should again be the same. Last and count should be the same because I'm filling sequentially from 1 using row count. Next, now let's take a look at filling the collection non-sequentially. Get all the rows from the employees table. Assign the record to the employees list, but don't fill it sequentially. Instead, use the primary key of the table as my row number or index value. As long as my index values are unique, this will work just fine. And the key thing here is that if I have the employee ID, then I can go to that record and get the information for that row of data very quickly and easily. All right, so I'm going to populate my collection non-sequentially, emulating my primary key. We'll take a look at the highest defined row number and the count of elements in the list, and then I'll demonstrate how I can go directly to an element in my list. I want to get the name, the last name for employee ID 138. Now instead of writing a loop through my collection looking for a match on employee ID, I can simply use the 138 as my index value because I used that when I populated my collection, use the primary key. I go to that location in my list and look at the last name. So no looping, no iteration required. Next, let's take a look at another way of filling the collection non-sequentially, but this time using the last name as the index. So remember, I declared two different types of collections. The second was index by employee last name, string indexing. So now what I'm going to do is for every record in my employees table, take that record, assign it to the employees by name list, and use as the index value the last name. I'll then display the last or highest defined index value. I'll then display the count of elements in my list of employees by name. And then I'll demonstrate that with a string index collection, if I have the last name of an employee, I can go right to that record in my list and display their employee ID, the reverse of what I showed you here. All right, let's run some code. So I run my script, and here's what I see. First of all, I filled my collection sequentially in two different ways. One was with count plus 1, and one was with row count. And as you can see in both cases, the last and the count are the same. There are 107 rows in the employees table, so the last index used is 107, and the count is 107 as well. Then I did my primary key emulation. And in this case, notice my last value is 206. It's higher than 107. Why is that? Well, as you will almost certainly find in your own tables, when you use a sequence to generate the next value, the next primary key value, you often end up with skipped values, maybe because of deletes in your table, or because of the way that sequences are buffered, allocated and buffered. But easily, the primary key values that are in use in your table are not sequentially allocated for one or densely filled. There might be gaps. So my highest primary key value is bigger than 107, but the count is still 107. Notice I was able to do my direct access to my employee ID 138. It looked up the last name Styles. And then I filled sequentially by name, indexing by name. And when I look at the last for the employees by name, that's funny, it's not a number at all. It's Zlatki. This is the last name of the person whose name is alphabetically last in the list. So the sort order of the character set determines what is highest and lowest within your index values in a string index collection. Notice also that the number of elements in my collection is 102 rather than 107. And what this means is that my employee last names are not unique. There are in fact only 102 distinct last names. Now usually when you choose an indexing scheme for your collections, you will be aiming, hoping, requiring that your indexing scheme is unique. In other words, every value, every individual string used to do the indexing is a unique value. In this case, last name is not unique, so what it means is that I overwrote the previous values several times, 5 times. Notice Oracle doesn't give you an error. It's not going to check to see whether or not that element already exists and say, no, you've already used this, that's a violation of your primary key or anything like that. This is a programmatic data structure. If you need to make sure that they're unique, you need to write the code yourself. For example, you might say, well, how can I do that? Suppose I did need to make sure that these things were unique. I could do something like this. If employees by name dot exists, so the exist method will tell me whether or not an element already exists at this name. So I could say, if it already exists, then display duplicate value, duplicate last name. So I could display the fact that there was a problem, else, and if. Let's try this. Let's grab this one block of code. Oh, no, it's hard to run separately. Let's run it all again. I run my script. And notice, 5 different duplicates. So I can write the code to guard against duplicates and do something about it, but it's something I have to do myself. Oracle will not do it for me. And finally, I do a direct access to the employee with the last name style. So just as I could use my primary key to quote-unquote look up the record for that employee and then get the last name, with the string index collection, I can do the same thing in reverse. So if I have the last name, I go to that location in my collection of records, indexed by last name. This is a record. This is the employee ID of that record, and there it is, 138. So hopefully it's pretty clear to you by now that you can go well beyond simply doing collections indexed by integer, filling them sequentially row by row by row. You can emulate primary keys. You can use string indexing. There's an awful lot of flexibility when you're working with associative arrays. And in fact, valid table of data types are virtually anything you can declare in a PL SQL program as a data type you can use as a table of data type. So all the scalar types, including booleans, collections of object types of records, collections of other collections, which are nested collections, which I'll talk about in a separate lesson. What you can't do is have a table of cursor variables or a table of exceptions. So those are two, excuse the pun, exceptions to the rule. Let's take a look. So here's an example of trying to create a table of sysref cursor variables. A cursor variable is a variable that points to a data set, a set of rows and columns. And here's a table of exceptions. So I can declare something to be of type exception, but it doesn't mean that I can use it as a data type in a collection. And in fact, I cannot. When I try to run either of these two scripts, index tables of cursor variables are disallowed. Notice the old name index tables instead of associative arrays. And encounter the symbol exception when expecting one of the following. So in this case, it simply told you this data type is not allowed. In this case, Oracle simply said that's not acceptable from the standpoint of even the syntax of writing PL/SQL code. But for all the normal kinds of data types you're going to work with, strings, dates, numbers, booleans, other collections, records, object types, you're okay. You can create collections of those elements and manipulate them. Let's talk a little bit more about valid index values. So I've talked before about how you can index by integer or by string. So what is the actual valid values that are allowed for these index values? First of all, there is no practical limit to the number of elements you can define in an associative array. In fact, the definition at the beginning of this talk talked about an unbounded list. Well, it's unbounded from the standpoint of practicality. There actually is an upper limit to the number of elements you can define in an associative array. The index values, the integer index values that are allowed in a PL/SQL collection range from -2 to the 31st plus 1 to 2 to the 31st minus 1, which is the same range as the binary integer data type. Now, that's about 4.3 billion elements. There is no way that you're ever going to create a collection with that number of elements or even close to it. Before you get there, you will blow out the memory in your session and your program will die. So that's why, from a practical standpoint, there is no limit to the number of elements that you can define. The theoretical limit is well beyond what you will ever achieve in your code. String index values can have actually any value. So if you're defining an index by string, you can use Smith, Jones, etc., etc. There's no specific range of values that is defined, only the maximum number of elements allowed in your collection. So you can use any string you want, but you can only have up to this many different strings used in your collection. Again, you will never reach that limit in practical day-to-day work with a collection because you won't have enough memory in your session. So you can use any string value you want for indexing. Let's take a look at the AA limit script to get a better sense of this and to see some rather odd behavior from Oracle. So I've declared an associative array of dates. There's my variable based on the type. And I'm going to use a small subprogram called setDate. I take the index value and I try to assign sysdate to that location in my list of dates. If nothing went wrong, I display no problem. Otherwise, I trap the exception and display the error message, format error stack. So what I'm going to do is pass in the limits. 2 to the 31st minus 1 is the highest value allowed. 2 to the 31st should be too high. -2 to the 31st plus 1 is the documented lower limit on an associative array index value. I'll try one below that, and I'll try another one below that. And then I'll try to set the value to null. I run my code, and here's what I see. Let's pull this up a bit. Okay, so try to assign a value to 2 to the 31st minus 1, no problem. Try to assign a value to 2 to the 31st, and it says numeric overflow. You're not allowed to use a value that big. Assign a value of 2 to the 31st plus 1, no problem. Now here's something curious. Assign a value to index value -2 to the 31st, not plus 1. This is actually officially outside the range of binary integer values, but Oracle doesn't make a fuss. Only if I reduce 1 past that does it give me a numeric overflow. So here's a little bit of a discrepancy between the documentation and the practical usage, or the way that the collections work. I can use -2 to the 31st as an index value. I would essentially avoid it if I were you, in case you ever even think about using index values like this, because this could be the kind of thing that Oracle fixes in the future. Finally, if I try to assign null, use null as an index value, Oracle raises the -6502, the value error exception, saying that null index table key values, so index values can never be null, whether you index by string or by integer. A little bit more details on the valid index by types. So the index by clause defines how you index the contents of your collection and what values you can use to find the elements in your collection. You can index by binary integer or any of its subtypes, including PLS integer, var char2 with an n between 1 and 32,767. You can %type against var char2 database columns, and you can use subtypes as well. Let's take a look at the various possibilities. So all of these are valid. I can index by binary integer, by PLS integer, which is the most common way that you'll see the indexing expressed, because PLS integer is theoretically more performant, faster than binary integer. Positive and natural are variations on binary integer. Positives are 1 and above, natural 0 and above. Hey, and there's even something called sign type, which is a subtype of binary integer. And the valid values for a sign type are -1, 0, and 1. So it's used for directional purposes. It'd be kind of strange to declare an array on that type, but it's allowed. I can index by varchar2s. I can index by table.column%type if the column referenced is a varchar2. I can also index by %type against other variables. And I can even declare a subtype which gives another name to an underlying base data type. And I can index by that. So all these things are allowed. What's not allowed is if I try to index by an integer column type or number column type in the database. So if I try this, well, first of all, let's compile all of this and make sure that there's no problem. So Oracle has no problem with any of that. But if I put this one in, it tells me implementation restriction, unsupported table index type. Now the reason for that is that it's true that employees, the employee ID is a data type of integer. See, it says number 6. Since there's nothing to the right of the decimal point, that means it's an integer. And even though number 6 is within the range of the binary integer, basically as far as the PL/SQL compiler is concerned, this is a number data type and not a subtype of integer. And the possible range of values exceeds the binary integer range. So if you're going to do a %type against a database column, you can only %type against string columns for string indexing. So even though, for example, I might be indexing by my primary key, let's go back to my original example of collections of records. Here I'm saying that I'm going to index by my primary key. I can't literally write the primary key definition here as I can here for my last name. So either you would put a comment. I might say indexing by primary key to let people know that that PLS integer is the primary key. Or even better is to create a subtype. So I can say subtype, the emp primary key type is integer. And then I can say, sorry, is PLS integer. And then I can right here say this, index by the employee primary key. So now I'm documenting in my code that the index by is the primary key. I'm hiding the fact that the actual data type is PLS integer. But at least now my table definition, my collection definition, tells you what the indexing scheme is all about. So lots of different ways to index by. Generally speaking, you'll mostly index by integer, in which case you just say index by PLS integer. Indexing by string offers lots of interesting possibilities, and I have a separate lesson just on that topic to explore it in great detail. So to draw some conclusions, associative arrays are the oldest type of collection, can be used from within a PL/SQL block only, and they offer a very high degree of flexibility. You have a large range of integer index values, both positive and negative. You can choose between integer and string indexing, and again we'll explore the possibilities for string indexing in a separate lesson. And sparseness, the ability to define index values non-sequentially in your collection, allows for easy emulation of primary keys and unique indexes. And that gives us some tremendous advantages when we want to copy data, usually copying data from a database table into a collection and then finding the values in that collection very quickly without having to scan through the entire contents of the collection. Well, I hope you've enjoyed this lesson on associative arrays and now have some ideas about how you can apply it in your own code. And hopefully you'll enjoy and get as much out of the lesson on nested tables and V-arrays.